So for the example 3.8.1, we are given a displacement field. UI is equal to cx2, cx1, and 0, where c is a constant, and ai's are initial coordinates. So assuming a linear strain, we find A, the Lagrangian strain quadric, B, the Lagrangian principal strains. Okay, so the first thing we have to do perhaps is to analyze what this means, no? So this is another way of expressing your displacement field UI in terms of what do you call this? These are the components of your vector. It's not a vectorial equation, but rather a vector component. Okay? Okay, so how do you now transform this into a vectorial equation in terms of a displacement field, no? So since these are separated by comma, it simply means that your u1 is this part here, your u2 is this part, and your u3 is 0. Okay, so we can now say that your u1 is simply equivalent to cx2, and your u2 is simply equivalent to cx1. And your u3 is 0. Okay, such that if I make use of my derivative, so this is what form is this? This is in the Lagrangian description. Okay, so how do I get this Lij? This is an infinitesimal strain tensor, okay, because there is no product term there. So I use the small deformation theory in this regard. Okay, so what's now the partial derivative? An L11 here, what's the partial derivative of u1 with respect to x1? It's 0, okay? So partial derivative of u1 with respect to x2. Sorry. If I have an L12, what's the partial derivative of u1 with respect to x2? Okay, so this is c. Okay, and if I have a partial derivative, an L1 3, what's the partial derivative of u1 with respect to x3? So that's 1, 3, it's 0. Okay, and so on and so forth. You just get, of course, if you will change the partial derivative here, this is 1/2 plus 1/2. That's why it became a c here. Okay. Okay. Let me write it so that we won't be confused. Okay. Let better if we write. I'm having problems with. Okay, if I have an L11, this is 1 half. Okay, the partial derivative of U1 with respect to 1. So this is 0 plus the partial derivative of U1 again with respect to 1. So this, okay, so this is 0. Okay, and if I have an L12, so this is 1 half. Okay, the partial derivative of U1 with respect to 2 is C. Okay, plus the partial derivative of U2 with respect to x1 is C. So this becomes, okay, okay, if I have an L13, I have again 1 half. The partial derivative okay, of U1 with respect to 3 is 0 plus U3 with respect to 1 is 0. So this becomes 0. Okay. So, tama na yung tatlo, no? 1, 1, 1, 2, and 1, 3. Okay, how about the other? So, let's go to 2, 1, 2, 2, and 2, 3. Okay, so partial derivative of U2 with respect to 1 is again C. Partial derivative of 1 with respect to 2 is again C. So this is simply C. So 2, 1 is C. 2, 2 is 1 half. Partial derivative of U2 with respect to 2 is 0, 0. So this is 0. 2, 3, partial derivative of 2 with respect to 3, 0 plus 0, so 0. Okay, so 2, 2 and 2, 3 are there. So ito na lang tatlo. Okay, so L 3, 1, L 3, 2, and L 3, 3. Okay, so this 1 half, 0 plus 0, 3 and 1, wala. 1 and 3, wala. 0. So 3 and 2, wala. 2 and 3, wala. And this is 1 half, 0 again, plus 0 equals 0. Okay, so that completes our matrix. So this is the one. So detalyado na yun, ha? So the string quadric is therefore simply this one. So you just make use of consists of I, L, I, J, consists of J. Okay, so you get this one. or simply this is equivalent to k squared. Okay? So this is your strain quadric, which represents the surface of the quadric. Okay, so this is the equation of the quadric surface. So the Lagrangian linear principal strains are given by the determinant of this. So you can use invariance if you want, no? But this is easier. If I use a determinant of the eigenvalue equation, I simply get this one, and I get the principal strains to be C, 0, and negative C. If I use the strain invariance, I will be doing a lot of formula, but it will lead to the same result above. And that's it. No? So we obtain now your, what are these again? These are these principal strengths. Okay, so mamaya baka yun ang gagamitin natin sa stretch ratio. Hindi na niya kinuha. So maybe you can use this to solve for the stretch ratio later. So for letter C, we are given the Eulerian linear strain tensor in a continuum as follows. Okay, so your Eulerian strain definition EIJ is given by this. So we are asked to find the relative or simply the direction matrix for a set of prime axis yi prime such that the y1 axis is rotated about the y3 axis at an angle of 90 degree coincidence with y prime 1 axis. So if we draw this transformation, so this has something to do with the transformation. So if I look into an x okay, so this is E, let's use Y. If I use a Y1 here, a Y2 there, so where's my Y3? Y3 is pointing towards us, no? So this is a Y. Okay, so where are my prime axes? So this is my prime axis. Okay, sorry, rotated so if I rotate the coincident with the y prime 1 axis about the y3 axis. So this means that my y1 axis is coincident about the y3 axis carries the y1 axis with the y prime 1 axis. Okay, so what happens here is you have here a 90-degree rotation. Okay, so if this is y1 and this is y prime 1, 90 degrees, your y2 prime must be here. Okay, so that's the description given to us by the transformation. I'm now stressed with my graphics tablet. So this is y2 prime. And y3 prime is coincident with y3. Okay, so this is y1, rotate it there. Okay. So let's now have the angle, no? The direction cosine. So what are my angles now? So if I have here my cosine or my theta ij, so I make use of my 1 going to 1 prime, so this is 90. Okay, 1 to 1 prime, it's 90 degrees or pi over 2. Let's use 90 na lang. And then 1 to 2, 1 to 2 is 0. Okay, this 1 to 1, then 1 prime to 2 is 0. So this is 0 degrees. And then 1 to 3 is 90 degrees. Okay, and then let's go to 2. 2 to 1 is 180. Okay, so I cannot draw the figure because my pen is, so you just follow. No? I'm really having a hard time writing it. Okay, so that's 2 to 1. 2 to 2 is 90. And then 2 to 3 is 90 also. And then 3 to 1 is 90. And then 3 to 2 is 90. And 3 to 3 is 0. Okay, so if I take the cosine of 90, 0, 0 is 1. Okay, 1, and then 0, negative 1, 0, 0, 0, 0, 1. Okay, so that's my transformation matrix. Okay, from the formula, E prime Rs equal to ARI AS JEIJ. So this is a transformation formula I already discussed to you in the analysis of stress. So this can be better manipulated by simply using the matrix multiplication. But I'd like you to change this to this one. So there's an error here. So it's an AE, A transpose formula. So this is your A here. E is this one, and A transpose is this one. And you get the rotated tensor in terms of this. So I did not place it in detail, but if you want to do it in MathCAD, you just write it as this, and you just symbolically perform the matrix multiplication, you will arrive with this answer. So I think there's a missing note here on trying to find the stretch. Okay, so A, B, okay, so anyway, you just try to get what is the stretch value if at a certain point. Of course, the given values for y, the coordinates y must be given in order to solve for the stretch. Okay, so you can solve the stretch ratio or the right stretch assuming a point P. Okay. Okay, so maybe you can try that. Just think about it, how to solve it using the principles I described. Okay, thank you very much for listening.